Hi, welcome to lecture 23. This is a lecture about surfaces and their areas. So we are moving up in our complexity of our objects. We're now talking about two-dimensional surfaces floating in three-dimensional space. We're going to look at those and compute their areas. More specifically, we're going to find parametrizations for those surfaces, but we're not going to tackle the general problem for all surfaces. That's too difficult. We're going to concentrate on three kinds of surfaces for this class that you should be able to produce parametrizations for. Those are graphs of functions, parts of spheres, and surfaces of revolution, all of which you've encountered in some context. We want to see what they all have in common and put them in the context of parametrized surfaces. And then we want to compute surface integrals. All right, so much like we did line integrals, which we were adding up functions over curves. Now we're going to add up functions over a surface, one of these new objects. So those are only two kinds of those, one with respect to surface area, and then with a vector field. And those are flux integrals. The last one we'll probably punt till next week. We'll stick with just the first for today. That's enough to cover. So let's dive in. So remember that a curve, it's the image of a function that goes from the real line R into multidimensional space, right? So we saw it in the plane for n equals 2. We saw it in 3 space for n equals 3, and you can make higher dimensional ones. But recall that we have the curve is the set of points in space, and then the parameterization is the function that maps a parameter onto there, right? Often t. There. So a parameterized surface is similar. It's the image of a function, but now the input has two variables, right? Two parameters here. So we talk about a function from the plane R2 into multidimensional space. And we'll just talk about n equals 3 for this class. That's rich enough, and we can picture it. So good old. Taking a piece of paper here, all right, we can embed this paper in three-dimensional space in all sorts of configurations that are fun. Those are the objects that we're going to study. So more formally, they typically take the form, right? R we call the function, the input or u and v, those are the parameters, and then to specify, right, a position for each one, for each value of u and v, we really just need three functions, right? X, y, and z, and those become the three components of the position of the point on the surface there. So together, this parametrization sort of puts coordinates down on our surface. By talking about u and v, you're talking about different points on the surface. Here. Look at two quick examples here. Here's a parametrization of the cone, right? So here we think of u and v as playing roles like x and y do in graphs of functions. But more specifically, so here's the domain in the UV plane, right here. It's just a circle there. And then what happens? I map each one to its place in the XY plane, but then Z gets this function, right? Square root of x squared plus b squared, which is just distance from the origin over here. And so the result, right, the output points of this function form a cone, right? This upper part here. You can also see some interesting structure here in the way this one is graphed. You'll notice that if you fix u, say, and let v vary, what you get is a function from one parameter, v, into space. So that's a curve. Right? And you see that here. Fix u and let v vary. You get these blue lines here in the UV plane. And then you map them over, right? Fix u, let v change. You'll get a curve, and it's these blue lines, right, that run along the cone here. So this picture is nice. You see the points of the cone. You also kind of see the parameterization in here, right? That u runs along one direction and v runs along another. Here's the same surface parameterized differently. Just like curves can be parameterized multiple ways, forwards, backwards, slower, faster. Surfaces can be parameterized multiple ways, and there the options are even more huge, right? The number of options for how to parameterize a surface. So here's another parameterization, same surface, because it's the same set of points, the same cone over here. But now u and v, right, those parameters are kind of taking on different meaning. Here you can kind of see that u is taking on the role of distance from the origin now. So it's like polar coordinates here. And v is playing the role of an angle, right? So v goes from 0 to 6 pi. and it gets wrapped around here. So these blue lines, right, for a fixed u, we see circles, right, in the plane. And then for a fixed v, these red lines, we see these radial lines going up the cone that way. So again, I'll show you. Right. So here's one parameterization where we got a grid sort of where u and v are perpendicular, rectangular, rectilinear, I suppose. And here where u and v are kind of playing the role of polar coordinates there. Okay, all right, but those are just examples. Let's be more specific about what I expect you to be able to do. So there are three kinds of surfaces I said we should be able to parameterize, right? They're graphs of functions of two variables, and those we've seen before. When I gave you a function of two variables and I said, let's picture its graph, you picture a surface in three-dimensional space, right? X and Y are the inputs to my function, and the Z component is the output. And then surface of revolution, right, which you likely saw in Calc 2 when you were computing volumes of different solids here. But now we're talking about surfaces, so you take a curve and you rotate it around an axis, and so then you get a three-dimensional surface in three-dimensional space. I think of this as like the pottery surfaces, where you've got a potter's wheel and a lump of clay, and you form the edge of it. Like that's the function that defines it, and then the radial symmetry gives it three-dimensional shape. And then parts of spheres, right? That's handy. Modeling our globe where we live, right? We tend to live on the surface of the Earth, most of us, and so you want to model parts of that, right? You want to parameterize the surface. It's good to be able to do that, and we'll just use spherical coordinates to do that. All right. Okay, so let's start somewhere. Let's start with graphs. So again, a graph of a function, it's the set of points in space of the form z equals f of xy. So little f is a scalar function of two variables there. Its graph is a surface in three-dimensional space. And so if you want to parameterize that, you simply take your two parameters u and v, and you map those to x and y, right, directly. And so this is in some sense, the most trivial way to parameterize a surface. And so you see right here, u and v are my parameters. So x becomes u, y becomes v, and z is the value of the function, the output value of the function, f of u and v. So it's fairly trivial to do, but you can make some cool shapes out of this one. So here's a graph of a fun function over a rectangle. Let's see, u goes from -2 to 2, v goes from -1 to 1. So it's just a rectangle in uv space. And then you map it over onto the graph this way. You get this bumpy arch shape. Okay, that's one example. The other ones are surfaces of revolution. All right, so these are surfaces generated by taking a graph, like so a curve in a plane now, right? Y equals g of x. You see here, right? It's that set of points is a graph of a function in a plane, and then you rotate it around an axis. So here, for example, around the x-axis there. And so how do I parameterize that surface here? Well, you take your two parameters, and their meanings will be fairly specific. One parameter, say u, will track along the axis. Right? So here I've got a function that I'm rotating around the x-axis. You see that here, the x-axis runs horizontally there. So u will take on that role, right? Track where you are along the axis of rotation. And then v will simply track the angle around, right? Because we're going to take our curve and wrap it around our surface here. And so then g, right, this function here, its role is its values become the radius of those circles right here. So I'm hoping that this picture makes some sense here. So if you fix a u, you pick a position along the x-axis, right, then, and you watch v vary, it's just going to make a circle, right, because I'm going to revolve this thing around the x-axis. The radius of that circle is the value of the function g at u. Right? So you fix u, that fixes a position along x. G of u tells you the radius, right? And then v, by varying, takes you around that axis here. So we'll look at fun examples, like trying to model things like this American football here in class. And then lastly are pieces of spheres. These are not too mysterious. If you remember your spherical coordinates, you can just have u and v play the role of the angles. Right? So we have the phi with like the angle off the z-axis, and theta, the usual angle around the z-axis here. So in this setup for a parametrization of a sphere, I've got u playing the role of v and v playing the role of theta, and I've got rho equals 1 here, right? So this is a sphere of radius 1. Yeah. And so you can get for a particular range on u and v some piece of the sphere. The only challenge here is just making sure your bounds on your coordinates match what the piece you want. So here they both go from 0 to pi over 2. I see. And so it makes sense. We get the piece in the first octant, right? Piece of the unit sphere in the first octant by limiting u from 0 to pi over 2 and v from 0 to pi over 2. All right, if you can handle those three, you'll be fine for this class, and you can handle a large class of surfaces parameters. Okay, super. So now, ostensibly, that we know how to parameterize surfaces, or at least what a parameterization looks like, we can get into computing surface areas, right? How do we measure area of a surface? This is a more interesting question than you might look like at first glance. Right? So you're probably, hopefully you're thinking by analogy, we did arc length for curves, right? And we integrated ds along there. And so what did we do? We chopped up our curve into little line segments, measure the length of each line segment, right? Add them up. There's your arc length. And so we're going to do something much like that for surface area. But the intuition about the length of lines is we think of having a string tracing out the path, and a string that doesn't stretch, right? And then by just maneuvering it and straightening it out, we can measure it, right? And that's what we mean by arc length, right? That makes sense. For surfaces, then you might think, okay, I've got some surface, right? Some bendy surface in three-dimensional space like this, and I want to measure its area. I'll just flatten it out, right? Measure the area. But that doesn't quite work so well for surfaces. For the ones where I bent a piece of paper, it's fine. But even simple things like spheres, you can't do that. And you know this if you've ever looked at a map of the Earth, of the globe. You probably know something about the various projections you can have, right, to turn a spherical object, right, still two-dimensional but spherical, into a flat, right, sheet. It turns out it's impossible to match it, right? It's impossible to map a sphere onto a sheet and have all the areas be accurate, right? Surely you've seen the map, where Greenland looks like it's the size of South America, and that's not quite the case. All right. Anyway, so one thing is surface area is a little funny from our perspective, though. Calculus is still powerful enough. We're not going to have a problem doing it, and we're going to do it really in a simpler way. We're going to zoom in on our surfaces, and then we'll model them with flat things. So, we can get around this flattening issue. But if I take a surface like this and I zoom in on it, I just want to add up all the little pieces of surface area I find here. Right? And we know that for differentiable functions, and indeed for smooth surfaces, if we zoom in, we're going to see planes. Right? So if our x, y, and z functions are regular enough, they are differentiable, or continuously differentiable, say, then we know that the surfaces, when I zoom in, will look flat at small scales. And so I can approximate areas by using the regular tools of calculus I have. So here's where the only part where some formulas will come into discussion. So let's talk about this point right here. I want to approximate the area of this little piece of my surface. All right, so even though it looks flat, it's probably bends a little bit. So the area is approximately, I'm going to call it delta S. All right, is the approximate area of this thing. So how am I going to model the area of this guy? Well, I do something clever. I realize that at any given point, if I fix one of my parameters and let the other one vary, I'll get a curve through that point here, right there. And then what I can do for that curve is I can differentiate that curve to find a tangent vector. Right. And so that tangent vector, I'm going to use the notation if r of uv r of uv is my parametrization, then this tangent vector, how do I get it? I freeze v and take the derivative as u varies. I'm going to use the notation here, ru. Here. Right. And what is that? Right? What is that thing? So it's a vector now. It's going to be tangent to my surface because it's tangent to a line in the surface there, but it moves along the u direction, right, this way. And then I can do the same trick going the other way. I should give you a formula for this, right? What is this guy? It's a vector, and it's just exactly the partial derivatives of each of the components. So that's x sub u, the u derivative of x, the u derivative of y, and the u derivative of z. There. And then I have another tangent vector in the other direction by fixing u now and letting v vary. Right? I can take its derivative, and you'll guess what that formula is. There's no mystery to it. Right? So this is another function at each point u and v. I can get this vector, and it's just the other partial derivatives, right? xv, yv, and zv. Okay. So I've got these two vectors there, and so what can I do with those these two vectors? Well, they model, right? I can use them to model the change of the curve along each direction. In particular, by multiplying by a little change in u for this guy, right, its derivative, and a little change of v of this guy there, I'll get two vectors that trace out the edges of a parallelogram here. So I'm going to write here to I remind you of a formula that we saw once upon a time, but the two vectors that form the edges of these parallelograms are exactly ru delta u, so times a little delta u, that's vector times scalar, all right, and rv, of course, times delta v. This is linearization where we take our two tangent vectors to the plane, and then may recall if I've got the two edges of a parallelogram, right, as vectors, I can find the area of that parallelogram, right, cleverly by just taking the cross product, right, and then finding the magnitude of that. Right, so remember the magnitude of the cross product, it's the multiple of the magnitudes times the sine of the area between them. That exactly gives you area of a parallelogram there. So, right, what that means is by differentiating our parametrization in each variable, we get the edges of a little parallelogram. Right, we take the cross product of those two and take the magnitude. We get a little piece of surface area. If we add this up, right, over all our u's and v's, of course, that's going to be approximately surface area. Right. So what's the moral of the story? Right. So in surface area, when we translate from Greek to German, we find out that ds, a little piece of surface area, it's given by this, right, quantity here, right, which will pop up, which is fascinating, will pop up a few times in a few contexts, times du dv. So you should see this as sort of a stretching factor, if you like. So your parametrization maps the uv coordinates into three-dimensional space. This guy here is a scalar, right? It's a little complicated how you get there, but when you're finished doing it, when you finish computing it, it is a scalar, right? Ru is a vector, Rv is a vector, cross products a vector. Magnitude gives you a scalar. That scalar tells you how much a little square in the uv plane gets stretched when you map it over by r. Right? So it's very much playing the role of the magnitude of r prime in arc length. Right? That tells you how much a curve gets stretched when you move it into space. This tells you how much a little piece of area gets stretched. Right? That's it's a rather neat formula. Anyway, you can just memorize this, and then we get a formula for surface area, right? Double integral of ds. So this is our first surface integral we're going to see. I use a double integral sign, and I use a little symbol to specify a surface. I use omega a lot, but you see others using other letters for it there. But that's the general form, much like a line integral has a general form, right, of one integral over c here. And then to compute it, we do a UV integral, right? So here's the definition of surface area, right? But to compute it, I use the parametrization, and I end up doing a plain old double integral in u and v, right? So here's my iterated form of that double integral. So that's how we compute surface area. I end up just computing exactly, right, the integral of this over my parameters, u and v. Here's a quick example just to verify that this spits out what we want. So let's start with a really simple surface. Here, a cylinder, radius r, height h. All right, so there's a picture of my cylinder here. So little r is the radius out here, and h is this, right, this dimension going this way. We know what this surface area is just by inspection here, but let's make sure our formula kind of follows this along. So what's the parametrization of that guy? It is a surface of revolution, right? It's a simple one, but still a surface of revolution. U track our position along the x-axis. The radius is fixed, right? We're rotating a constant function around the x-axis here. So r is a constant, right? And then we just have cosine v and sine v to track us around in the y and z coordinates there. We have some bounds on u, right? U goes out to h here, and v wraps all the way around, so that's right, 0 to 2 pi. And so let's compute. Here are our two derivatives. I take the u derivative of each component, right? That's very simple. I get 1, 0, 0, right? These guys do not depend on u. I take the v derivatives, right? Slightly more interesting. I'm missing an r there. Let's fix that, all right, before I forget. There, it's a constant, but you can't forget about it. Here, there's the there's the derivative of v, right, rv. And so now let's take the cross product, and let me make sure I did this more correctly. I'm forgetting my constants. Let's put them in, fix it as we go. So there's my cross product. It would turn out it's quite easy when you take a cross product with one, right? With 1, 0, 0. It's fairly trivial to compute, right? And you can even check that these guys are orthogonal to one another. And more importantly, the length of that guy, again, it's not 1, it's r. Just so silly. All right, here. And finally, we get our thing. So where did that r come from in the answer? That integrand should have just been r. Okay, all right. Now, this is correct. So when I compute my surface area, I integrate just in my u and v coordinates, right? This stretching factor, though, is exactly the radius, right? It's in u, it was directly, right, laid things down directly in u, but with v, things got stretched exactly by the radius. So you end up with 2 pi r h, right? That's the perimeter of my circle times the height, exactly what you expect to get. Right. Okay, so this is the procedure you should follow as you do this. One thing I didn't mention that is probably worth doing, this step here is a good time to pause. You should also put in the right delimiters here. This is a good time to pause after you've computed RU cross RV, right? It's always a good time to just pause and say, okay, does this make sense? Have I computed have I computed things correctly? Do I have a vector here that makes sense? And what should this vector do? Well, RU, remember, is tangent to my surface. RV is tangent to my surface. And if I take a cross product, I get something orthogonal to both of them. So this vector here should be orthogonal to my surface. And that's going to be very useful in the future. For now, it's just a mechanism to check that you've done things right. Right? Is this thing orthogonal to my surface? And if you look at it, it does make sense here. It has no x component, and minus r cos v minus r sine v. Those are exactly the negative coordinates of the point on of the y and z coordinates. So it points in, right? So I take my surface, look at it again. My RU cross RV will point in. It's orthogonal to the surface, so it sounds like we did things correctly here, and we did. For surface area, though, we don't need a direction, right? We just need the magnitude of it. But it's good to think about direction at this stage. All right, so there's our computation of surface area. And so to finish this off, general surface areas, right, there's nothing more we need where we can put a scalar valued function into the integrand. So this is the general form for a surface integral of a function with respect to surface area. So the where here, right, is the parametrized surface we've been talking about, so sitting inside of R3. Right? The vector R maps U and V onto that surface, but the U and V occupies some region in the plane, right, on R2. The what is a scalar field. That's the integrand. So that's defined in three-dimensional space, right over there. We often think of temperature as a go-to here. Maybe you want to find the average temperature on a surface of something. You would integrate, you would do a surface integral of temperature there. But we'll see some other applications of these functions. We'll see densities, right? So you've got a varying density of some surface you want to compute. Mass, certainly, charge density, right, and probabilities as well. And we'll see examples of those. And then the how, right, is the with respect to surface area here. And so here's the formula. Looks like a whole lot of letters, but we can understand all of this. How do we compute one of these guys? So I've got a surface integral over omega of f with respect to arc length. Right here, the what, the where, the what, and the how in there. And so what do? You turn it into a UV integral, right? A double integral in UV space. And so you do a composition, right? You map your U and V's into the space. You then evaluate f at those points. So that's just a composition here. I get a scalar out of that. And then there's that stretching factor, right? Because I want that scalar times a little piece of surface area. So again, I get the magnitude of RU cross RV here, right there, that's stretching factor. And then you just integrate out in U and V, right? And you get an answer. So you get a scalar out of this thing. So just like a line integral, we move it to a T integral, right? A surface integral, we move to a UV integral. There you have it, a lot to swallow, and drive it home. You have to do dozens of examples. We'll do a bunch in class, and I will see you there.